Q61. According to MuleSoft, which principle is common to both service-oriented architecture, SOA, and API-led connectivity approaches? A. Service centralization. B. Service statefulness. C. Service reusability. D. Service interdependence. The correct answer is C. Service reusability. Explanation. Why C is correct. Reusability is a foundational architectural principle shared by both service-oriented architecture, SOA, and API-led connectivity. Both paradigms focus on decomposing complex systems into modular, self-contained services or APIs that can be easily discovered, shared, and reused across multiple business capabilities to eliminate point-to-point redundancy and reduce integration costs. Why A is incorrect. Modern architecture patterns, including API-led connectivity, advocate for decentralization and distributed governance rather than rigid service centralization, which historically created bottlenecks in ESB architectures. Why B is incorrect. Both SLA and API-led design principles strongly emphasize statelessness over statefulness to maximize service scalability, availability, and fault tolerance. Why D is incorrect. Service design principles strive for loose coupling and independence rather than service interdependence, ensuring that changes to one service do not break dependent downstream applications. Q62. An external web UI application currently accepts occasional HTTP requests from client web browsers to change, insert, update, or delete inventory pricing information in an inventory systems database. Each inventory pricing change must be transformed and then synchronized with multiple customer experience systems in near real time, in under 10 seconds. New customer experience systems are expected to be added in the future. The database is used heavily and limits the number of select queries that can be made to the database to 10 requests per hour per user. What is the most scalable idiomatic used for its intended purpose? Decoupled, reusable, and maintainable integration mechanism available to synchronize each inventory pricing change with the various customer experience systems in near real time? A. Write a Mule application with a database on table row event source configured for the inventory pricing database with a watermark attribute set to an appropriate database column. In the same flow, use a scattergather to call each customer experience system's REST API with transformed inventory pricing records. B. Add a trigger to the inventory pricing database table so that for each change to the inventory pricing database, a store procedure is called that makes a REST call to a Mule application. Write the Mule application to publish each Mule event as a message to an Anypoint MQ exchange. Write other Mule applications to subscribe to the Anypoint MQ exchange. Transform each received message, and then update the Mule application's corresponding customer experience systems. C. Replace the external web UI application with a Mule application to accept HTTP requests from client web browsers. In the same Mule application, use a batch job scope to test if the database request will succeed, aggregate pricing changes within a short time window, and then update both the inventory pricing database and each customer experience system using a parallel for each scope. D. Write a Mule application with a database on table row event source configured for the inventory pricing database with the ID attribute set to an appropriate database column. In the same flow, use a batch job scope to publish transformed inventory pricing records to an Anypoint MQ. Write other Mule applications to subscribe to the Anypoint MQ. Transform each received message, and then update the Mule application's corresponding customer experience systems. The correct answer is B. Add a trigger to the inventory pricing database table so that for each change to the inventory pricing database, a store procedure is called that makes a REST call to a Mule application. Write the Mule application to publish each Mule event as a message to an Anypoint MQ exchange. Write other Mule applications to subscribe to the Anypoint MQ exchange. Transform each received message, and then update the Mule application's corresponding customer experience systems. Explanation. Why B is correct. This scenario presents a strict database constraint. Polling is limited to 10 select queries per hour, which makes any interval-based database polling mechanism incapable of meeting the less than 10-second near real-time synchronization requirement. Using a database trigger/store procedure to immediately push event notifications via REST to a Mule API avoids database polling entirely. Publishing these events to an Anypoint MQ exchange implements a classic publish-subscribe, pub/sub pattern. This decouples the inventory database from target systems, ensures high scalability, and allows new customer experience systems to be added in the future simply by binding new queues to the exchange without modifying producer flow. YA is incorrect. The on-table row listener relies on continuous polling queries against the database table. Because the database strictly restricts select queries to 10 per hour, polling cannot achieve near real-time sync, less than 10 seconds. Furthermore, using scatter-gather tightly couples the inventory flow directly to each customer experience system API, making it difficult to maintain as new systems are added. YC is incorrect. Replacing the user-facing web application with Mule application does not address the fundamental need for event-driven distribution to decouple downstream systems. Additionally, batch processing in parallel for each scopes introduce unnecessary complexity and tight coupling rather than utilizing a message broker for pub/sub decoupling. YD is incorrect. Like option A, using a database on table row event source requires frequent database polling that violates the database's strict limit of 10 select queries per hour. Q63. How are the API implementation, API client, and API consumer combined to invoke and process an API? A. The API consumer creates an API implementation, which receives API invocations from an API such that they are processed for an API client. B. The API consumer creates an API client, which sends API invocations to an API such that they are processed by an API implementation. C. An API client creates an API consumer, which receives API invocation from an API such that they are processed for an API implementation. D. The API client creates an API consumer, which sends API invocations to an API such that they are processed by API implementation. The correct answer is B. The API consumer creates an API client, which sends API invocations to an API such that they are processed by an API implementation. Explanation. Why B is correct. In MuleSoft and general API terminology, the API consumer, an organization, developer, or business entity, owns or builds an API client, such as a mobile app, web application, or back-end service. The API client sends requests/invocations over the network to the exposed API endpoint, where the requests are received and processed by the underlying API implementation, the Mule application logic, flows, and back-end connectors. Why A is incorrect. The API consumer does not create the API implementation. The API provider builds the implementation to handle requests sent by client applications. YC is incorrect. An API client does not create an API consumer. Rather, human developers or organization consumers develop and register client applications clients. YD is incorrect. This incorrectly states that the client creates the consumer entity, reversing the real-world relationship where consumers build and manage client applications. Q64. An insurance company is implementing a MuleSoft API to get inventory details from the two vendors. Due to network issues, the invocations to vendor applications are getting timed out intermittently, but the transactions are successful upon reprocessing. What is the most performant way of implementing this requirement? A. Implement a scatter-gather scope to invoke the two vendor applications on two different routes. Use the until successful scope to implement the retry mechanism for timeout errors on each route. B. Implement a choice scope to invoke the two vendor applications on two different routes. Use the try-catch scope to implement the retry mechanism for timeout errors on each route. C. Implement a for each scope to invoke the two vendor applications. Use until successful scope to implement the retry mechanism for the timeout errors. D. Implement round-robin scope to invoke the two vendor applications on two different routes. Use the try-catch scope to implement retry mechanism for timeout errors on each route. The correct answer is A. Implement a scatter-gather scope to invoke the two vendor applications on two different routes. Use the until successful scope to implement the retry mechanism for timeout errors on each route. Explanation: why A is correct. To retrieve inventory details from two vendors in the most performant way, parallel processing is required. The scatter-gather scope executes calls to both vendor endpoints concurrently across separate routes. Wrapping each individual route inside an until successful scope ensures that if one vendor endpoint experiences an intermittent network timeout, only that specific fail request is automatically retried without blocking or re-triggering the request to the other vendor. Why B is incorrect. A choice scope acts as conditional logic, if/else, to execute only one matching route based on a DataWeave expression, making it impossible to query both vendors simultaneously to gather complete inventory. Details: why C is incorrect. For each scope processes elements sequentially on a single thread rather than in parallel, which significantly degrades performance. Furthermore, wrapping the entire loop in an until successful scope would reinvoke successful vendors during a retry triggered by a single failed vendor. Why D is incorrect. A round-robin scope alternates routing between endpoints across successive flow executions, load distribution, rather than executing both routes in a single request to fetch aggregate vendor inventory. Q65. A leading e-commerce giant will use MuleSoft APIs on Runtime Fabric, RTF, to process customer orders. Some customer-sensitive information, such as credit card information, is required in request payloads or is included in response payloads in some of the APIs. Other API requests and responses are not authorized to access some of this customer-sensitive information, but have been implemented to validate and transform based on the structure and format of this customer-sensitive information, such as account IDs, phone numbers, and postal codes. What approach configures an API gateway to hide sensitive data exchanged between API consumers and API implementations, but can convert tokenized fields back to their original value for other API requests or responses, without having to recode the API implementations? Later, the project team requires all API specifications to be augmented with an additional non-function requirement, NFR, to protect the back-end services from a high rate of requests according to defined service level agreements, SLAs. The NFR's SLAs are based on a new tiered subscription level, gold, silver, or platinum, that must be tied to a new parameter that is being added to the account's object in their enterprise data model. Following MuleSoft's recommended best practices, how should the project team now convey the necessary non-functional requirement to stakeholders? A. Create and deploy API proxies and API manager for the NFR. Change the BSRL in each API specification to the corresponding API proxy implementation endpoint and publish each modified API specification to Exchange. B. Update each API specification with comment about the NFR's SLAs and publish each modified API specification to Exchange. C. Update each API specification with shared RML fragment required to implement the NFR and publish the RML fragment, and each modified API specification to Exchange. D. Create a shared RML fragment required to implement the NFR, list each API implementation endpoint in the RML fragment, and publish the RML fragment to Exchange. The correct answer is C. Update each API specification with shared RML fragment required to implement the NFR and publish the RML fragment, and each modified API specification to Exchange. Explanation: why C is correct. MuleSoft advocates a design-first approach where API specifications serve as the single source of truth for both functional and non-functional requirements, NFRs. The idiomatic modular way to convey reusable requirements, such as rate-limiting SLA tiers, gold, silver, platinum, across multiple API specifications is to define a shared RML fragment, such as a trait or library. Referencing this fragment in each API specification and publishing both the shared fragment and the updated specifications to Anypoint Exchange ensures that all stakeholders have clear, version-controlled, and standardized access to the API contract. Why A is incorrect. Deploying API proxies in API Manager and changing the base URL represents an implementation and deployment step rather than a contract design step. Stakeholders must review and understand non-functional requirements via the API design specification before implementation occurs. YB is incorrect. Adding informal comments to RML specifications is a poor governance practice. Comments are unparsed text strings and cannot be programmatically validated, governed, or parsed by tooling into structured traits or policies. YD is incorrect. RML fragments are designed to contain reusable types, traits, or resource definitions, not environment-specific runtime implementation endpoints. Hard-coding individual endpoint URLs inside a shared design time fragment creates tight coupling and violates separation concerns. Q66. A Mule application is being designed to receive nightly a CSV file containing millions of records from an external vendor over SFTP. The records from the file need to be validated, transformed, and then written to a database. Records can be inserted into the database in any order. In this use case, what combination of Mule components provides the most effective and performant way to write these records to the database? A. Use a parallel for each scope to insert records one by one into the database. B. Use a scatter-gather to bulk insert records into the database. C. Use a batch job scope to bulk insert records into the database. D. Use a DataWeave map operation and an async scope to insert records one by one into the database. The correct answer is C. Use a batch job scope to bulk insert records into the database. Explanation: why C is correct. The batch job scope is MuleSoft's built-in mechanism explicitly engineered for processing high-volume, larger-than-memory datasets. It splits the incoming dataset into individual records, stores them on persistent queues, and processes them asynchronously across threads. Combining a batch job with a batch aggregator allows records to be grouped into blocks and committed via a single database bulk insert operation, drastically reducing network round trips and maximizing write throughput. YA is incorrect. The parallel for each scope processes iterations in parallel in memory on separate execution threads. For a CSV containing millions of records, attempting to split and insert records one by one rapidly leads to memory exhaustion and out-of-memory error, database connection pool starvation, and severe network latency. YB is incorrect. Scatter-gather is designed to route a single input message concurrently across multiple independent processing paths, parallel branching. It is not designed to split and iterate over millions of records from a flat file. YD is incorrect. While an async scope moves execution off the main flow thread, inserting millions of records one by one using a map transformation still results in millions of individual database round trips, creating immense performance bottlenecks. Q67. An organization is implementing a quote-of-the-day API that caches today's quote. What scenario can use the CloudHub Object Store connector to persist the cache's state? A. When there is one deployment of the API implementation to CloudHub and another one to customer-hosted Mule runtime that must share the cache state. B. When there are two CloudHub deployments of the API implementation by two Anypoint Platform business groups to the same CloudHub region that must share the cache state. C. When there is one CloudHub deployment of the API implementation to three workers that must share the cache state. D. When there are three CloudHub deployments of the API implementation to three separate CloudHub regions that must share the cache state. The correct answer is C. When there is one CloudHub deployment of the API implementation to three workers that must share the cache state. Explanation: why C is correct. When a single Mule application is deployed to CloudHub across multiple workers' replicas for high availability or performance scaling, CloudHub Object Store, specifically Object Store v2, serves as a persistent, centralized key value store. It enables all workers running the same application deployment to share and access a single, synchronized cache state across workers. YA is incorrect. Object Store partitions in CloudHub are scoped to CloudHub applications and cannot be directly shared or accessed natively by an application instance running in a customer-hosted Mule runtime. YB is incorrect. Anypoint Object Store v2 partitions are isolated per application deployment. Separate CloudHub application deployments across different Anypoint business groups cannot natively share the same object store partition directly via the standard connector. YD is incorrect. CloudHub deployments in separate geographic regions represent independent application instances. Object Store v2 is scoped to a specific application deployment within its target region, so separate regional deployments cannot directly share an object store partition instance via the object store connector. Q68. Refer to the exhibit. A business process involves two APIs that interact with each other asynchronously over HTTP. Each API is implemented as a Mule application. API 1 receives the initial HTTP request and invokes API 2 in a fire and forget fashion, while API 2, upon completion of the processing, calls back into API L to notify about completion of the asynchronous process. Each API is deployed to multiple redundant Mule runtimes and a separate load balancer, and is deployed to a separate network zone. In the network architecture, how must the firewall rules be configured to enable the above interaction between API 1 and API 2? A. To authorize a certificate to be used both APIs. B. To enable communication from each API's Mule runtimes and network zone to the load balancer of the other API. C. To open direct two-way communication between the Mule runtimes of both APIs. D. To allow communication between load balancers used by each API. Q69. In Anypoint Platform, a company wants to configure multiple identity providers, IPs. For various lines of business, LOBs, multiple business groups and environments have been defined for these LOBs. What Anypoint Platform feature can use multiple IPs access the company's business groups and environment? A. User management. B. Roles and permissions. C. Dedicated load balancers. D. Client management. The correct answer is D. Client management. Explanation. Why D is correct. In Anypoint Platform, client management, configure via access management and API manager, allows an organization to configure multiple external identity providers IDPs, such as Ping Federate, Okta, OpenAM, or custom OAuth/ODC providers, across different business groups and environments. This enables different lines of business, LOBs, and environments, e.g. sandbox, QA, production, to enforce custom authentication and client credential authorization for client applications requesting access to their APIs. YA is incorrect. User management handles platform developer/administrator login authentication, single sign-on/identity management, and user account creation within Anypoint Platform, rather than controlling how external client applications request and validate API tokens. Across business groups and environments, YB is incorrect. Roles and permissions govern RBAC, role-based access control, within the platform, defining what users can see or execute in Anypoint Platform, but do not serve as a mechanism to register or manage external IDP configurations for API clients. YC is incorrect. Dedicated load balancers, DLBs, handle network routing, custom domain names, and SSL/TLS termination for Mule runtime environments. They are not involved in managing identity, provider integrations, or client application credentials. Q70. What is the MuleSoft recommended best practice to share the connector and configuration information among the APIs? A. Build a Mule domain project, add the database connector and configuration to it, and reference this one domain project from each system API. B. Build a separate Mule domain project for each API and configure each of them to use a file on a shared file store to load the configuration information dynamically. C. Build another system API that connects to the database, and refactor all the other APIs to make requests through the new system API to access the database. D. Create an API proxy for each system API and share the database connector configuration with all the API proxies via an automated policy.
If this video helped clear up these MuleSoft concepts for you, please hit that like button and subscribe to the channel. It really helps support the content. But don't go anywhere just yet. Stick around and jump straight into the next video to keep building your integration skills.